Hello, everyone. We welcome you today to Where Did My CPU Go webinar. This webinar is presented to you by Enkitec. We certainly appreciate you taking time out of your day to join us for this webinar. I'd like to also introduce our sponsor of this event. Our sponsor is Redgate. Redgate is an organization out of the UK that Enkitec has formed a partnership with. They develop a variety of tools that are very useful for DBAs and developers with over 600,000 users worldwide. I'd like to refer you over to their website. You can learn more about Redgate by visiting the website that you see on the slide now. They also manage a website by the name of allthingsoracle.com. This is a resource center for Oracle users. So I certainly encourage you to visit that website. Some of you may be very familiar with it. That may have been how you heard about this webinar. So without further ado, I'd like to introduce our presenter today, Karl Arao. He is a senior consultant here at Enkitec, and I'll let him take it from here. Thank you very much for joining.
Thank you, Damaris, for the introduction. And for all the viewers, thank you for attending this webinar. So let's start. Oh, before anything else, so why the title? Where did my CPU go? Simply because for the past 2 or 3 years that I've been with Enkitec, I've been doing a lot of server sizing and consolidations, and whenever we get engaged by a customer, they would immediately ask us how many let's say Exadatas do we need to buy, or how many CPUs do we need to have for our environment, right? So for me to be able to tell them that, let's say, oh, you only need half rack, or you only need quarter rack, or let's say 60 CPUs out of your workload. I mean, for me to be able to tell them that, I need to know the behavior of the CPU, how it works, right, and how to administer. They'll be coming from different hardware platforms, or let's say just CPU speed differences, right? And by knowing all of that, then I'll be able to model their, let's say, end capacity or utilization moving forward. So that's the driver of this research. All right. A little bit of introduction. I'm Karl Arao, and I'm a senior technical consultant at Enkitec, and I'm a performance and capacity planning enthusiast. I have 7 years plus DBA experience, so I'm getting older, so I just need to put plus on my years of experience. So I am an Oracle ACE, OCP DBA, and I'm an RHEE, and I'm an Oak Table member. I do blog, and I have a wiki, and I do tweet as well. I work for Enkitec, and we have a presence in North America and EMEA. We have over 70 plus staff, and we mainly do Exadata, BI, Apex, and training. The books at the bottom are some of the books that we've written. And this June 2 and 3, we'll be having this specialized conference just for Exadata and big data. It's called E4. So it's more like a hot sauce for Exadata. So if you're more into that kind of technology and related technologies about big data, then that's the conference for you. So for our agenda, the agenda would be it's just 4 parts. So first, I'll establish. So basically, there are 2 halves of this presentation right here. So this is more of the hardware side. I'm giving you more of like a foundation on the hardware side of things, because if you're doing sizing, and let's say if you're pulling workload data from those servers, you need to know how those server behaves and how to compare speeds across those servers, right? And then after I've given you the foundation on the hardware side of things, I'll be giving you more of a deep dive on the database side of things, right? I'll be showing you what's the different CPU events, and how to be able to have a consolidated view out of those databases that you're consolidating. All right. So let's start with this database parameter called CPU count. So essentially, the CPU count is the number of CPUs that your database is using. And that's actually boils down to the logical IOs, or no, not logical IOs, but logical CPUs that you have on your database server. All right? And this is actually the parameter that you set when you do instance caging. So let's say if you set the CPU count to 4, then that database or that instance will just make use of 4 CPUs out of that, let's say 16, right? So let's dive a little bit deeper on the CPU architecture of Xdata version 2. So it's 2 sockets, 8 cores, 16 threads. So 2 sockets meaning it has 2 physical sockets. So this is just one machine view of the Exadata version 2. So 2 sockets. If it says 8 cores, then each socket has 4 cores, which totals to 8 cores. And then for each core, you have a duplicate of that core. So if that duplicate is actually the hyper-threading technology. And for each socket, you got 8 threads or logical CPUs, which totals to 16 threads, right? That's just the pretty picture view of that CPU. But on the OS side, I've got this script called CPU Topology, and when you run it, it will show you this. Now, per row, it has a meaning. So the process source, that's essentially your logical CPUs. So let's say here it's showing you 16 CPUs. The physical ID, the distinct numbers on your physical IDs, that will be your sockets. So we've got socket 0 and then socket 1. For the siblings, you've got the logical CPUs per socket. So for here, I've got socket 0, and then it's got 8 threads, socket 1, and it's got 8 threads to totals to 16, right? And the core ID is just the core ID numbering across the cores. And then the CPU cores will be the number of cores that you have per socket. Totals to 8 cores. Now, I've been to some environments where the number of the siblings and the cores are the same. Now, if you see that kind of number, or let's say when you log into the server and you execute the script, if you see that those numbers are the same, then that means they turned off the hyper-threading, all right? On the later part of this presentation, I'll be showing you the performance effect of having that hyper-threading feature turned off, all right? And then another thing that I want to show you is this tool by Intel. It's called the turbostat. So what this thing do is if you want to instrument the thread level of performance and how it relates to the cores and the package or the socket, then this tool is very good to have. And it also shows you on your server or on your machine. So the Turbo Boost feature is another feature of the CPU where, let's say, it's more like an automatic overclocking of that CPU. So on the output of turbostat, you've got this essential or critical columns where this TSC is actually the advertised clock rate of that specific CPU. And this gigahertz right here is the turbo boost clock rate of that CPU. So turbo boost is actually more is important or is useful just for, let's say, 1 or 2 single-threaded process. And what happens is if you have just that running on your server, then the turbo boost will make that specific thread or core it will increase that clock rate of that specific thread or core, and it will it's pretty much like you're making the most out of the performance of that specific CPU, right? So it's automatic overclocking. So enough about the CPU architecture. Now let's do compare CPU speeds. So there are different methods of comparing CPU speeds. All right. First is if you're going to do publish benchmarks, and second is actually running the benchmark on that specific server. For the published benchmarks, there are three benchmarks that I usually use, but for most of the sizing, I use this spec int rate 2006. But just for completeness, I'm going to be discussing this tree. All right. For the actual benchmark, there are two tools that's available for you. The first is the CPU Toolkit, which I wrote, and it can be downloaded on my blog. And if you go here, CPU Toolkit, all right? And Slob, which is created by Kevin Clausen. So Slob has this LIO harness where it just saturates your CPU, and that's essentially the actual benchmarking is. You saturate all of your CPUs and see how many logical IOs you can do per second, right, up to the max. So first is TPCC. So it's made by Transaction Pricing Performance Council. The measure of performance is by throughput and price performance, right? So transactions per minute and dollar per transactions per minute. So when you go to the website, they've got these full disclosure reports, right? And on those full disclosure reports, it's got these headers, but we're only after the CPU performance. So that's why we normalize the transactions per minute by core, right? And on the next few published benchmarks, you will see more and more of this, of normalization by core, because we're after the performance of the core, right? And then from here, the FDRs, or full disclosure reports, they also have a page where it's all CSV files. So you can download that CSV file, put it in Excel, or let's say massage it on a, let's say, have this formula already when you massage the data. And, and then from there, you can easily grab that file. But for here, I'm just showing you how to do the division of the TPMC by core, which is the output of this is 100,000, which means the higher the number, the faster it is. All right. So the second is the spec int rate 2006, which is by Standard Performance Evaluation Corporation. And spec int rate measures the integer performance, which most of the softwares actually is just making use of integer calculations, right, or operations. And the good thing about this spec int rate benchmark is all of the CPUs are being used, because the previous versions of this spec int rate, they're just benchmarking one CPU, which is then by this processor advancements, it's not anymore relevant, right? So if you are saturating all of that CPUs and then comparing to the other platform that's saturating all of CPUs, then you can have that good comparison of performance, right? This spec int rate is used by OEM 12C consolidation planner. So Oracle uses this on their tool for consolidation, and it's being stored on the Sysman EM-spec rate live. So I'll just show you a quick view of this consolidation planner. So how does this consolidation planner uses the spec int rate? So let's say if I have two targets, right, and then that target will have an equivalent speed, and this target will have an equivalent speed, and both of those targets will have an equivalent utilization of that utilization. So that's the speed and the utilization are being accounted, so that let's say when you put it on a specific node, the end utilization will be something like this. All right. But what I don't like about consolidation planner is it just takes into account the host level utilization. so let's say for this guy right here, it's 69.8%, but it doesn't know how many databases are inside that specific box. So what we do when we do sizing, we break it down into, let's say, how many databases do you have, and get that specific utilization just for that specific database, so we can easily model it and play around with capacity planning. All right. So in spec int rate, the measure of performance is spec int rate per core. And on the website, they've got this big HTML file, or they also have a downloadable CSV where you can massage the data, right? And you just divide the peak by the number of cores that you have, which is this number, and the higher, the better. And so as I said earlier, when you have it on a, let's say, a massage format, where I've already done the calculation, you can easily grep and compare one server to another. All right. So I'll in a little bit I'll show you the spec power, but for this, I just want to show you how you can apply this on specific scenarios or comparison scenarios. So here I'm comparing 2007 CPUs to 2012. Now, so I've got this TPCC and spec int rate, right? Then these are the results of 2007. So for this, just focus your eyes on the first column, all right? So the first column is the TPMC per core, and it's the result per core for the spec int rate. So I'm comparing two platforms, the IBM and the Intel platforms. And back in 2007, the IBM is the fastest server at that time. And as you can see here, it shows that it's 100,000, and the Proliant ML370 34,000. All right. And if you look at the spec int rate, it shows you that it's 30 and then 18. All right, so the spec int rate reflects the performance gap on the TPCC as well. All right. Now let's move forward to 2012. So that's the TPCC, and that's the spec int rate behind this. Now, for the TPCC, you don't have any. Wait, let me just do this. For the TPCC, you don't have any TPCC result for the power servers, but then you have the results of everything on the spec int rate. So for the power server, it's rated at 45, and then the Intel boxes are rated at about 43. Now you would notice that this tree right here, the IBM, this Intel box right here, they are pretty much on the range of 45 to 43, right? So what does that mean? Then I can pretty much say that in 2012, these platforms are pretty much closing in on with the IBM platform in terms of CPU performance, right? And given that the spec int rate numbers reflects the TPCC result, then I can assume that this guy right here, the result will be probably around 100,000 as well, right? Or 100,000 plus, because this is higher than these two right here. All right. So I mean, that's how you make use of those numbers, and it's pretty handy. So also you would notice that I've got this right here, a Spark machine, right? Just to show to you for completeness that let's say, so for the Spark, they've got slow CPUs, but they've got a lot of CPUs. See that 128 compared to 16, right, on the Intel. So for this platform right here, so if you have, let's say, a specific need for, let's say, a highly threaded, let's say, workload, and you want a lot of logical I/O capacity, and the application is very sensitive with, let's say, the clustering. It doesn't want to be on a clustered node, right? Then this kind of server is right for you, right? Now, let me show you really quick. Let me go back. Let me go back to this slide, and I will show you really quick uh, the data set that I have for the spec and trait. So I've downloaded this file and I've put it on Tableau. So this is the result of spec and trait. And then I just want to show you the CPU speed through the years. All right, so this 2006 up to 2013. And these are different hardware platforms, right? So you can hack this data. So now what I'm going to do is I will color them by processor group. So you've got AMD, IBM, Intel, and Spark, right? So earlier on the slide deck, we were actually looking at the 2007 and 2012, right? So 2007, this green right here is your IBM, which is the faster server around that time, right? And through the years, as you can see from the previous slide deck, I told you that Intel is catching up in terms of CPU speed. So from the graph, it's really evident, right? So if I just split this into, let's say, processor groups and by year, so processor groups and by year at the bottom, so you can see here that the IBM and the Intel, let's say 2013, 2014, right? They're pretty much, on the same top in terms of speed, right? And then another interesting thing is this Spark platform. When they recently launched this T5 servers, um, so previously I was showing you this slow CPUs, right? When they launched that new platform, it's just a very big speed jump for that platform. So they came all the way from 18 to about 30. All right, so it's pretty much doubled performance, right? What else? Oh, let me show you really quick this spec power that I have. So spec power, on the end of this presentation, I've highlighted some books, and one of the books actually tells you how to make use of spec power just for energy efficiency comparison. But I don't really use this for sizing. I still make use of spec and trait for sizing because it's just CPU centric, right? It's just raw CPU performance, right? And when we size for database servers, we're really after the performance, right? But this benchmark right here, it's just showing you they only have AMD and Intel available on their dataset. And spec and trait, they have the 4 processor groups available for that specific dataset, which is pretty good. In TPCC, you've got lesser dataset because it's not just about CPU, it's a whole stack. You've got the storage and all of that, right? So for CPU centric, I would still use the spec and trait. So for here, for the spec power, so the measure here is server-side Java operations, SSJ, per watt. So you're measuring the energy efficiency of that specific CPU. So still, from this graph, Intel is still the winner, right? And if you normalize it by core, so let's say this is a 4 core, 8 core, right? And then it's divided into AMD and Intel, right? So as you can see here, Intel is still the best in terms of energy efficiency. But then you've got this AMD where it has a lot of cores, and then for me, for let's say database, I would still go with this, which is high performance and low power than these guys right here, right? So it's just another data to look at when you're doing server comparisons. All right. So for the actual benchmarking. So the actual benchmarking is actually running a specific workload on your specific server, or on that specific server that you're looking at on migrating to, or let's say migrating from, right? So for the benchmark, you've got the CPU toolkit and slog. So for this example right here, um, it's both of them are this are the same box, right? So the difference with these two benchmarks is the way it behaves in terms of workload. So the CPU toolkit, it tends to saturate one thread at a time. So let's say if I run, let's say, start CPU of 1 and end CPU of, let's say, 8, it will saturate 1 on the first cycle, and it will saturate 2 on the second cycle, and then 3 on the third cycle, and it will go on until it saturates everything, right? For the slub, so let's say if it's, let's say, run init, let's say 8, so let's say if 2, 4, 8, then what it will do is it will saturate it across the CPUs as you give more drivers to that specific, let's say, driver script, right? So having this, let's say, difference in workload is still very beneficial. Let's say if you are benchmarking or analyzing a specific, let's say, scenario where, let's say, for me, I want to analyze what's the difference of if I turn off the hyperthreading or if I turn off the turbo boost, right? So it's still best to have different views and a consistent, let's say, test case when you do your changes, right? Now, for here, I want to apply the specific benchmark result, right, running actually on the server so this is the by running the actual benchmark on the server and making use of that for server migration, right? So let's say here I'm just comparing the V2 and X2. The V2 is this, which means the 2.1 million. So it's saturated all of the 16 CPUs of that server right here. And then for the X2, it saturated all of that CPU of that specific server, 24 CPUs. Now, this right here will be your, let's say, speed. So 2.1 and 3.6, right? That's your performance comparison between those two platforms, right? Because it was only able to attain, let's say, 3.6 million logical IOs per second and 2.1 million logical IOs per second. Now, making use of that number for, let's say, a migration scenario is, let's say, very beneficial, because let's say if you have this, let's say, transactions per second and the utilization of your host source machine, you can, so with the numbers that you have for the speed comparison and these utilization numbers, you can estimate what will be the end utilization on your target machine without even doing the migration itself, right? You just need a few basic simple math, and you'll be able to arrive pretty much, at the same utilization as you would do the actual migration. So let's move on to that. So first, what you would do is you have to get the what I call the chip efficiency factor, which is more like the CPU speed, all right? And the source logical IOs per second would be the V2, which it only attained 2.1 million, and the destination would be 3.6, right? And then dividing that will be 0.58. What's the meaning of that? It means that the one CPU of the version 2 is equivalent to 0.58 of the X2. All right, because X2 is a much faster CPU, that's why you only be needing this much CPU. Now, the next thing to do is apply that speed factor and multiply that to the number of CPUs that you're using on your source box. So here I got the 0.58, and I'm multiplying it to the source host source host CPU multiplied by the utilization, which makes it 7.36, which means I'm just using 7 CPUs out of the 16 CPUs. Now, if I multiply that with the speed factor, then I'm only getting 4.29 CPUs. All right, and after that, I will multiply that 4.29 to the capacity of the X2, which is 24 CPUs. And then once I divide this, I'll get this 17.8%. So if I do the actual migration, all right, you see the utilization, it's pretty much close to the 17.8, right? So why? Because you're essentially migrating from slower CPUs to faster CPUs. As you can see from the SQL drivers, so the response time is 0.006. When you migrated to the faster CPU, the response time, it went to 0.003. Right? Essentially, what happened here is, let's say you've got this workload on the V2. Now, when you migrated to the X2, it got cut, halved into half. So you got this X2 right here, right? So you're now making use of or you're making use of less CPUs because you're migrating to faster CPUs. Now, this headroom that you gained by migrating from V2 to X2, so here you're doing 1,200, right? So you have more headroom for more transactions per second, right? So you can double your, let's say, transactions per second because you essentially gained that headroom by migrating to faster CPUs. So let's say this can be about 2,000 range, right? And then still get that specific or the same amount of utilization that you had from your previous server, right? But then you're making more transactions per second. That's the beauty of the capacity planning math behind this, and being able to forecast it without even doing the migration, right? Let me let me show you something. Now, what we do is I'll show you this tool. So we have this tool that we use because you already have the capacity planning formula, right? Now we want to we have this sizing. We have this tool where we have the sizing. We have this tool where we have our sizing process built in on this tool, where let's say if we'll be migrating from if we'll be migrating a bunch of databases, we want to be able to account for their speed differences, right? So normally we send them extract scripts, and the extract scripts will give us the workload of those databases, and then from here the customer will already have, let's say they're already seeing on, or they're already looking into purchasing a specific configuration. So we would put that here. Let's say it's a quarter rack, right? And then from there, we would lay out, let's say, how many databases they're expecting to migrate across that quarter rack. And then after that, we will be able to see that visually, the overall utilization and the recommended hardware for that workload across the CPU memory and storage size, right? And then from there, we will be, let's say, we'll be able to tell moving forward how many months will it take them to reach the 75% utilization of their specific cluster. So I showed you a simple scenario where we are migrating from V2 to X2. Now, but here we are using the actual workload numbers, right? So what if we make use of that, right? So let's say I have a, so because this is uh, an X2 environment. So it's 2.25 racks. So it's 2 nodes. The speed is so let's substitute this first with this real actual values. So the X data speed of this would be 3.6, right? And then the number of CPUs for that specific configuration is 24. All right. And then my source machine, it will have 16 CPUs, and no, it will have 16 CPUs, but the speed of that specific machine is 2.1. So let's say let's put it here, 2.1. And then the CPU utilization, or the number of CPUs that this server is using, is 46%. So I would put 46% right here. And you see the result, it's 18%, which is pretty much just the rounded off value of this, right? Now, if I don't have this actual benchmark numbers, then I can go to spec int rate and get the spec int rate and get the specific speed of that specific server, right? So let's say here I've got an X2 quarter rack, so my speed would be 26, right? And then on the V2, my speed would be 16. Now, if I make use of spec int rate, I'm still pretty close to the utilization of what's utilization of how it is if I make use of the actual benchmark numbers, which is pretty cool, right? And I can also make use of this to do high level estimations. So let's say you have an M9000 box, right? So let's say you have an M9000 box. It's one big giant box, and then let's say on one good day you just decided to, hey, I want to migrate to X4 let's say -8 full rack. How much would it take, or how many, or let's say how many nodes, or how would it look like if I migrate this whole thing to this X4-8 full rack? So from a high level point of view, because this guy right here will have a bunch of databases running on it, right? And then it will make use of specific workload, right? So, but for high level, I would just assume this to be using the 100%. And then how would that 100% look like on this target environment? So I can easily do that with this capacity planning math that I showed you. So here, so let's say this, and I'll be using spec int rate, for example, for this example. So the spec int rate of M9000 is 14, and it's got 256 CPUs. So let's say I'm laying it out on, let's say, a full rack of an X4, right? Eight nodes, 39 speed, and 48 CPUs. Now, from the graph, it shows me that if I migrate one M9000 box to an X4, then it will be about 23% or 24% CPU utilization. And with that, I'll have about 61 months to be able to reach 75% utilization, which is about 5 years, right? So, but here I still have a lot of headroom. I still have a lot of free. So with this, I can just, let's say, oh, I may be able to migrate my other M9000 box to this configuration. So, I mean, with that capacity planning format I showed you, you can easily model how it would look like without even doing the migration, right? So I can, let's say, oh, I'll still be able to fit another one from this configuration, and then see that let's say new machine on a high level or cluster wide perspective, and you can play around with this. And let's say if I fail 2 nodes, what would happen to the rest of the nodes? Let's say, right? So here, when I failed the 2 nodes, all of the other servers went to 96%, right? And and but the high level utilization did not change, right? It's because all of that resources went to the other remaining nodes, right? So that's the beauty of this capacity planner formula. Now, this is just the V2 and X3, X2, this should be X2, and X3 comparison, all right? And let's move ahead with this cores versus threads. Now, this is a pretty complicated graph, but then this is very useful for explaining the CPU behavior of when it gets to a point where it's very saturated. So I'll discuss 3 points on this graph. First is the default, right? And what if I turn off the turbo boost? And what if I turn off the hyper threading, right? So the default behavior where everything is turned on, right? How it works is, let's say this is a 1 socket, 4 cores, and 8 threads. Let's say I have here 8 threads, and I've got 4 cores in it, right? The default behavior is, what usually happens is, let's say if you saturate the whole box, once you get past the cores that you have on your server up to the max number of threads that you have right here, you're only getting about 20%, 20 to 30% of speed increase up to the max number of threads, right? And that also varies, depends on the workload. But then you're not getting linear performance. You're not getting linear performance out of this hyper-threaded CPUs, all right? That's the default behavior. And later I'll show you something about the instance caging, where normally you would set it at the 75% area of this total CPUs that I have. So so what happens to the sessions when it goes to this specific area of performance? So as you saturate more and more CPUs, when you reach the maximum number of threads that you have, you started to experience CPU wait, meaning you're already running on run queue, right? So for this driver, the driver SQL that I have here, it's 1 second per execution. Where if I, let's say, saturate it up to the max number of CPUs that I have, and at this point, I have more and more sessions sharing this nonlinear CPU capacity right here, right? So at this point, right, my 1 second elapsed time is already 1.2, which is the 0.2 is waiting on CPU wait, right? That's what happens when on the session level numbers. And as I saturate more and more CPUs, the more I will be waiting on CPU wait, or the more of the CPU wait will be the component of my response time, right? But what if I, let's say, turn off the turbo boost? So if I turn off the turbo boost, then as I said earlier, it just matters for 1 or 2 single-threaded processes, right? So that's just what it is. But when you start to, let's say, saturate more and more CPUs, or all of it, then it doesn't really matter anymore, right? It's just pretty much the same. Even though the turbostat will show you that it's still doing the clock rate increase, it's not really giving you anything. So for the hyper-threading, so if I turn off the hyper-threading, so this is hyper-threading turned on, and this is hyper-threading turned off. So if I turned off the hyper-threading, what happens is I lose all of my threads, right? And then at that point, as I saturate, let's say, more and more CPUs, then after the course, because I don't have any more threads, right? So after that, I'll start to experience CPU wait right away. So with the hyper-threading turned on, so here with the hyper-threading turned off, you experience the queuing effect earlier, right? And it's bad for your response time. But for this, with hyper-threading turned off, you're experiencing it on a later stage, right? Even though you're not getting any linear performance out of this, completely avoiding the CPU weight still helps on the standpoint of performance, right? So that's how you explain the CPU behavior. So that 30% really depends on the workload, right? So we got the CPU toolkit and the slob, and it shows you the difference on behavior of these two, which is here it's pretty much conservative that I've only got 17% performance out of this workload, and here it's 21%. There's an Intel white paper that actually specifically tells you that you're only getting 30%, but then it's variable depending on, well, it shows you on my test case, right? So read on this, it's pretty good stuff. Oh, and by the way, what I was saying earlier is when I do instance caging, I would just set it to this 75% area where everything is pretty much still predictable, right? Because here, as I'm doing more and more work, I'm sharing more of that CPU cycles with other sessions, and I'm not getting any more faster, right? I'm just saturating the box. So normally, I would just set it at the 75% area. So what do I mean by 75% area? So let's say if you have 48 CPUs on the box, then 75% of that is 36. If you have 3 databases on that box, then set each of them to 12 CPUs, 0.75, right? 36 divided by 3. So set each of them to 12 CPUs. But then there's a MOS note that actually tells you, let me do this. I have a tool for that, CMOS. All right, there's actually a MOS note here, this doc ID, that actually tells you that you must set it to just about 75%, right? And this guy right here, this note right here, doesn't really explain really well why you have to set it at 75%. So my test case right here that I've shown you, I've just quantified that MOS note that you have to set it at 75, or you can actually what do you call that, over allocate, right? Meaning you can have let's say one database that's having these 12 CPUs, and then the other one has 20, right? Given that you know the workload of that specific database, that it can go as high as 20, and not, let's say, the other 2 database that you have that's set to 12, not let's say content with that 20 CPU count that you have on that database. Because if all of that becomes active, then you have you're asking more than what you have on your capacity, right, which is 48. So yeah, so let's move ahead with this different CPU events. So we're already done with the hardware side of things, and I've already given you that hardware foundation. Now we're moving on with the different CPU events. So there are 3 different CPU events. It's called the CPU wait, and CPU scheduler. So the CPU is more of like the CPU is the real CPU cycles. CPU wait is the time spent on one queue. CPU scheduler is the time spent above your CPU count. So let's say if you set your CPU count to 4 and you're asking for 6, right? So that difference of 6 to 4, you'll have 2, let's say, AAS on CPU scheduler, which I will show you to you in a little bit. So here, this is AES CPU. And just always remember that one AES CPU is equivalent to 1 thread that's 100% utilized. So for here, I've got 8 CPUs on my box, and I'm using 2 AES CPU, and this means I'm on my OS side, this will be 25% utilization when I execute, let's say, top or VMstat, right? Now, on the session level, you will on the session level or top activity page, you will see this 2AES CPU as well, right? But then, as you can see from the bottom, you've got 4 sessions, right? So, so how does that work? Well, 2AES CPU or 2 average active session doesn't always mean that you have 2 highly active sessions. It can be, let's say, 4 sessions contributing to this 2 AES CPU. So from here, I've got about this 1, 2, 3, and 4 contributing to this 2 AES CPU. Now the CPU weight. The CPU weight means it's the time spent on run queue. So from here, I increase the load to 10, right, to the 10 area. Now I got this load average right here, and there's a difference of, let's say, the instance foreground CPU with this load average. That difference is actually this. That's your CPU weight right here. So all of this CPU cycles are being spent on run queue. Now, on Ash, or on the top activity page, because the top activity page pulls from Ash data, it doesn't show you that specific light green graph, simply because Ash, let's say, even though you're out of CPU, it's still accounted as on CPU, right? But I would still go to the performance page just to validate this. But this workload right here. But pretty much, if you know that you have 8 CPUs on your server and you're making use more of that, then this is already running on run queue. So from here, the sessions right here, this section is mostly running on run queue, and this section right here are the only ones that are getting served by the actual CPU. So the CPU scheduler. The CPU scheduler is more of like the instance caging. So so if you implement instance caging, oh wait. So if you implement instance caging, so let's say here I've set the instance caging to CPU count of 4, then this drops to. So what does this mean is I box the Oracle kernel, the CPUs that the Oracle kernel can only use to about 4 CPUs, right? From a high level point of view, you're still asking for 10 CPUs, right? But only 4 is being served on the real CPUs. So this other area right here, they're just waiting and being capped by the resource manager, right? And you will also see that from the top activity page, that let's say this is just the area where all of those sessions are being served, and the area right here are being preempted by the resource manager. So the wake event will be resource manager CPU quantum. So putting this all together, these different CPU events. So let's say if you have a sudden plan change, and then that plan change contributed to, let's say, a high load average, or let's say this server of yours being 100% CPU utilized, and you don't have any instance caging turned on, then immediately you would see the CPU weight, right? And then once you've already logged on the server, then you can implement the instance caging, cap it to CPU count of 12. And then at this time period, you can do your troubleshooting, because everything is already under control, right? In terms of the Oracle and then on the OS side, because the load average just went down. And then from here, you implement the fix, and then you just, and then it goes back to the normal workload, right? Now, just remember that whenever you do instance caging, set it up to the point where it's just above the CPU workload that you have, or do characterization of your workload and set it to a point where you still have a headroom for spikes, right? So the last part is the CPU monitoring and capacity planning. Now, I've got this. So we'll talk about the tools to monitor the CPU, and we will talk about tools to be able to get a holistic view of that, or consolidated CPU view of a bunch of databases. But we will start with the OS side. So for the OS tools, there are different OS tools: VMstat, Top, MPstat, right? There are also cool tools. Let's say it's CollectL. CollectL outputs performance data on just one row. Let's say CPU, memory, disk, I/O, disk, and then there's this turbostat-C, where I've shown it to you earlier, where it instruments the per thread performance, and the turbo boost feature. Now, there's also this DCLI index data, where you can easily tell which nodes are saturating the box or the whole database, right? But in Oracle, there's this Oracle load map. The Oracle load map is like an enterprise-wide view of your load, right? And when you click on this, you will be it will go directly to the performance page of that specific database. But I will show you in the next few slides that there's a value of having more dimensions out of this specific data set, right, with the AWR analytics. So when you click on any of those boxes, you will be taken to this performance page. So I was telling you earlier that when you set the CPU count parameter, just go above that green line, right? So you have to do your workload analysis and take into account that specific CPU spikes, right? So that's the performance page, and it gives you real-time and historical view. But so I've got this AWR toolkit, which pulls AWR information across databases and consolidate them in one CSV or one big table. So what I usually do is, let's say on the customer side, I would run this extract scripts and then load it on my data warehouse on my laptop. So let's say each client will have their own dimension tables, and then from there I can analyze it with Tableau Analytics. There's another version of that script where you can download it from here, right? And it gives you the holistic view of your database. It captures top event, CStat, IO, CPU, storage, services, top SQL, more of like characterization of that specific database, right? You can download it from here. You don't have to create that warehouse anymore. It just outputs it in CSV files. You just have to aggregate that CSV file. Now, how do you make use of that CSV file here? So the CSV file is just really a CSV file. But Tableau makes sense of this dimension columns, where you have this distinct number of values right here. And you can only just drag and drop it on, let's say, whatever measures you have. So let's say here, this is the total number of CPU seconds that I have for that specific server, right? So I can have a dimension of that by instance or by hostname, right? I'll show it to you in a little bit. Another thing that's really cool about AWR analytics is this time dimension. So the time dimension with this the ability to easily drag and drop and do data exploration, the time dimension takes care of snap differences across databases. So let's say if you have 15 minutes or 10 minutes or 1 hour snapshots, and if you, let's say, combine them in one CSV file, whatever, let's say, measure falls on that specific time dimension, that will be accounted, and all of that will be aggregated in one 3D graph. And another beauty of this is you can always right-click and view data, and then from the view data, you can drill down on that specific data set. And then from that data set, you can say, oh, this is not really aggregating it correctly, so I may have to do some kind of aggregation, or let's say do max instead of average, right? So it's pretty cool for data exploratory purposes. So the visualizations that you can do here is something like this. So let's say this is a consolidated CPU view of a half rack Exadata, right? So let's say if it's got dimensions, right? So you can really just drag and drop things. So I will show you a really quick example, and then we will be wrapping up in a little bit. so um, so remember, we've got this tree map view. Sorry, we've got this tree map view um, where, so this is like the performance page, right? So what if you can actually drag and drop things where you can show, let's say, oh, I want to see a monthly view of that tree map view, right? This is cool right here. So what if I want to drill down of that tree map view per host name, right? But for capacity planning purposes, I, I mean, you'll just after this consolidated view of this specific resource, right? So this is the weight class of this bunch of databases, because if I, let's say, just drag it on the core, then it will show me the instance names who are the resource hoggers of those specific weight class, right? But just for the purposes of, let's say, CPU capacity planning, I would just filter the CPU weight, and then CPU scheduler. So I would filter all of those 3 CPU events, all right? And then from here, I already have my consolidated peak workload, right? So from here, I have this 70 CPUs. I'm asking the 70 CPUs at this particular workload period, right? So this works really well for a bunch of databases. So let's say here, I've got this another example where I have 120 or 100 something databases across, let's say, 39 host names, right? So if I consolidate, so they're essentially downsizing, and they want to determine how many exadatas or nodes do they want to will do are required to have, right? So whenever you're doing sizing, you always need to get the consolidated peak of those databases that you're sizing. So from here, I'm just asking for 120 CPUs, right? And then from here, I can just get the data out of this and put that on our tool and put it right over here. And then from there, it will model. We can pretty much easily model the capacity of those specific number of databases, right? Now let's go back to this half rack view. So from this half rack view, you can drill it down by server, right? So here you have a half rack view of CPU load, right? And then you can see here that you have this number 4 node. So this is 1 quarter. So you have this quarterly process that's overutilizing this 4th node. So from the point of view of load distribution, this view is very, very useful, because let's say you can do what you can do is, for every quarter, I can distribute these specific instances on nodes 3 and 2, right? So I'll be able to handle that specific workload spike, right? And then what you can also do is a lot of what-if scenarios. So let's say if we want to consolidate this database and this database right here, it will just automatically sum up that specific instances. So if I have 2 nodes and 2 nodes rack, what will be the requirement of that? And then in terms of CPU, so let's say if this is 48, all right, and then if I have x2-2 boxes, then I can just always divide it by the number of CPUs or capacity that I have. So it means this workload right here needs two servers, right? That's what you can do with AWR analytics. So I've already shown you the CPU usage per host, all right, and then I've already shown you the CPU redistribution across nodes. So I'd like to wrap this up really quick. So what I've shown you is I've shown you the CPU foundation. So how do you compare CPU speeds, right? And then I've shown you the different CPU events. And then how do you scale it? How do you scale the monitoring across multiple databases, right? By doing analytics, all right? So, uh, uh, and just to repeat that, I've shown you how to compare CPU speeds and showed you the cores versus threads behavior, the different CPU events, and the AWR analytics. And I've got this a bunch of resources and go through all of them. I have a white paper. It's a more detailed white paper. And then these are the books that I'm recommending for you to read if you're more interested on the capacity planning. And yeah, that ends my presentation. So if you guys have any questions, just feel free to email me on this email address. Thank you guys.